Well, hello. This is Sustainability Modeling Spring of 2013, lecture number 5. It's not me, it's you, or models of social interaction. Let me tell you the lecture outline for today. We're going to be looking at interaction between populations, and so far we in the class we've been discussing primarily, single stock models. This lecture we're going to introduce a number of multiple stock models and see how these different populations interact. We're going to be doing a little bit of math for that purpose, and we'll be introducing that as well. And we're going to be looking at a first type of interaction, which is referred to as the predator-prey models. We're going to be looking at a simple example in predator-prey. We're going to be doing an advanced version of a predator-prey model. We're going to be looking at the interaction between population and catastrophes and how how a catastrophe affects population at a given point in time and see how that changes the dynamics of the system. And then we're going to talk about another type of interaction between populations, which is epidemics and how epidemics, move over time. I think the first thing I'll say of interaction between populations that in terms of when we speak about populations, plural, those could be different species. Could be different cohorts or simply subgroups. We're going to be doing this in the most general of senses. And the key characteristics of these interactions is that the dynamics of each population are affected by the dynamics of others. So it's a mutual interaction. And today we'll focus on several types. We're going to be looking at predator-prey interactions, which are more competition between species. We're looking at catastrophes and epidemics. So let's talk about the predator-prey interactions. A simple population interaction of the predator-prey type was derived independently by two scientists, Alfred Lotka in the United States and Lotka-Volterra in Italy at about the same time. And the model that both of these came up with describes the dynamics of competition between two species. So these are two species competing against each other. And this essentially results in one species being able to grow at the expense of the other. Okay, and the species that is able to grow at the expense of the other we call the predator, and the one that gets grown upon or at the expense of, it's what we're going to be calling the prey. This model is mathematically described by a very classical set of equations that are referred to as the Lotka-Volterra equations. And I want to go briefly through them. The general idea is that we have two populations, X and Y. X is the predator population, and Y is the prey. And the dynamics, you have essentially two dynamic equations, one for the predator, one for the prey. And each of these dynamic equations has a plus and a minus term. The plus term, as we've seen before, is denoted to describe population growth, and the negative term is population decay. So in the case of the predator, the growth of the predator, it's driven by the availability of the predator and the prey, meaning basically that the more population of predator there is, the faster they grow, but also the predator needs the availability of the prey to grow. So therefore you have these what we refer to these second order dynamics and driven by this rate coefficient A. And we're going to be seeing a model of this later in this lecture, and we'll see what the numbers are. And then the predator has a natural, a rate of death represented by B. So and that causes the predator to decay. So those are the dynamics, the conceptual dynamics of the predator population. The prey, on the other hand, is also able to grow, and it grows naturally, and driven by a coefficient C. And then the death of, or the decay of the prey it's not only due to natural causes, but it's also due to the availability of the predator, X. That's why in the prey equation, the decay is driven by these second order dynamics. So those are essentially, that's essentially the essence of the Lotka-Volterra equations. Okay. Now, I like to rewrite these equations just to make have a better understanding of how these dynamics work. And essentially, if you just factor out a few terms, then you can recognize very easily that the first term on the right-hand side of the predator equation denotes that the growth of the predator is driven by the availability of prey. So the growth A times Y of the predator is proportional to the availability of prey Y. Okay. Similarly, in the prey, the death of the prey is driven by the population of predators. Okay, so the more predators there are available, the faster the prey will decay. Okay, so this leads to some interesting dynamics. Now, one useful aspect of looking at multiple species dynamics like this is that you can look at the concept of the equilibrium population sizes, and these are essentially, if these populations were to stabilize, what would be their values? And that they're found simply by setting the equations to 0. So basically, they don't change over time, and you can just set the right-hand sides of both equations to 0, and this allows you to calculate two values of equilibrium populations. One for the prey, y sub e, which is found as the rate b divided by the rate a, and another equilibrium population for the predator, x sub e, which is found by the ratio of constant c divided by constant d. Okay, that's some very simple, just setting to 0 the right-hand sides of the equations and solving for the population sizes. We can do a simple calculation, and let's imagine that we have a we're going to be working on this model later on in this class. Let's imagine that we have two species, foxes and rabbits, and given with these parameters, parameters A, B, C, and D, and notice the units of the parameters. A and D, which are the growth of the predator and the death of the prey, are second order units. So they have they depend on the other predator. And then B and C, which are the death rate of the predator and the growth rate of the prey, are independent, and they'll just have units of time. And let's imagine that we have an initial population of 100 predators, foxes, and 1,000 rabbits of prey. So let's just do that, and you can actually do a calculation. And if you do that, you can come up with equilibrium populations of, in this case, 667 rabbits and 150 foxes. So these are, if the system were to stabilize, these would be the the values of coexistence of foxes and rabbits given these dynamics. Okay. Now I'm going to fast forward. I'm going to show you some Vensim results. We're going to come back and run the Vensim model specifically for this case, but I did want to show you how the outcome looks like, and it's interesting that when you plot the predator and prey populations in a plot like this, you're going to see that they actually both have oscillations, and that's interesting. So the populations don't really stabilize, and this is interesting because in the population models that we discussed last lecture, where we had the carrying capacity and these concepts, essentially in all scenarios, what we saw is that the populations tended to stabilize after a while. Here, we're looking at over 1,000 years, and populations are oscillating all the time. So they go up and down. One thing that you'll notice is that they tend to oscillate around the equilibrium value. So if you look at the value for the rabbits, which was 667, it's somewhere in the middle range of the oscillations. And similarly for the foxes, the 150 population, it's in the range for the population of foxes. So that's interesting, and that happens because of this interacting dynamics of the two. Is that you're actually not able, populations don't really stabilize, but they actually oscillate over time. So if we can summarize this with a few remarks, first, there is an oscillatory behavior in both populations, and these oscillations are around these equilibrium population values. So there's really no static equilibrium. Rather, it's a dynamic equilibrium, meaning that you get the oscillations, and these oscillations are constant over time. The populations go up and down, and they do so over time. And it's interesting because this well-established classical result matches observations in many natural scenarios, and particularly when you have pure competition. And if you look at the large ecological reserves, in South Africa, or the Southern Africa, part of Africa in particular, you see that the populations of several species tend to go through these oscillations. They grow and they die, and then they grow again and die again over multiple years. When they're not intervened. So, and remember that these very simple Lotka-Volterra equations do not consider any type of intervention. No sequestering one species for food or for agriculture or anything like that. So these are really pure. It's pure competition between two species. Okay. So we're going to be looking at this model in a lot more detail, and we're going to be looking at two versions of predator-prey models. One which is the simple case, and then we're going to be making it a little bit more complex. So that's going to be part. I'll take you through part of today's lecture. The next the next type of interaction that we're going to be see later on in the modeling is epidemics, and epidemics are interesting, and some of the dynamics are similar to this predator-prey. The model that's used, there are a number of them, but there's a classical SIR model, SIR, for susceptible, infected, recovered model. And I want to basically flash a little bit the math here and just walk you a little bit through the equations, because we're going to be coming back to this specific example with the Benson model. But essentially, you have three state variables, or three control variables, which are the susceptible population, the infected population, and the recovered or recuperated population. Each of them has again a positive negative dynamic. So the positive means population is growing, and so in the case of the susceptibles grow as a fraction of the recovered, which means that some population that recovers from the illness can become susceptible again. Okay, and some models have this term, some don't, and I wanted to show you this one. And the susceptibles decrease because of the possibility of getting infected. Okay, so once they become infected, they're no longer susceptible; they become infected population. The infected individuals grow at the expense of the susceptibles, but they can recover. Okay, so there is an ability to be recovered, and that's a negative term in the infected equation. Okay, once an infected becomes recovered, it's part of the recovery pool, the recovered pool. And the recovered pool grows according to the dynamics of the infected. Okay, the recovered grow at the expense of the infected. So that's sort of the dynamic that's captured there. And and similarly to the predator-prey model, you have some alpha, beta, and gamma coefficients that are used to describe the rate of exposition to the epidemic, the rate of infection, actually catching the disease, and the rate of recovery, getting out of the disease. Okay. Well, we're going to move on and to the next part of the lecture, which is to look at the Vensim models. And we're going to be looking at four Vensim models that are here, the predator-prey, and each of these models has its link, so you can actually look at the video. So I'm going to be stitching all of this together in a single video lecture, but you can actually look at the individual videos for each of these cases in YouTube, and also, of course, if you want to view them offline, the videos will also be on Dropbox. So I'll be looking at the predator-prey, simple, the advanced, the catastrophe, which I haven't really talked about because the math, it's as you will see, it's a little bit of a combination of the other two, and the epidemics, which we just explained. So that's going to take us through the next to the next part of the lecture, and so we'll lead with that. Okay, in this lecture, we're going to look at four Vensim models for predator-prey. Two models for predator-prey, one simple, one advanced, a model for epidemics, and a model for catastrophe. So I'm going to start by looking at the very first one, the predator-prey simple model, which is the one that was covered in the lectures in class. And I'm going to fire up Vensim. I have a sort of pre-zoomed this model so it shows in the big screen, and I'll be toggling back. Let's take a look at this model here, and the first thing you'll notice is that it, like in the description that we did previously, it's got two stalks. It's got a predator population, and if you sort of hover over it, you'll see the units, it's foxes, and we're going to be looking at the unit and each of the dialog boxes in a second, but I wanted to go over first a little bit of the general structure. So you have a predator and a prey, and these are two stalks. Let's take a look at what goes into the predator. The predator has a birth rate, which we're calling predator net birth here in the model, and it's got a death rate defined by predator net death. There's an initial predator population, and there are rates of A and B that come into feeding the births and the deaths of the predator. Okay. Now the net birth of the predator, it's also dependent on the availability of prey. So you see an interaction between the population of the prey and the predator net birth, and we're going to take a look at how that looks mathematically in a second. And this is the same equation that we discussed previously in this lecture. If you look at the prey population, the prey population also has a net birth. It also has a net death, and the net birth population is driven by a constant C and by the availability of the prey, and the death of the prey is driven by a coefficient D and also by the availability of prey. Another distinction to make, again, is that the death of the prey is also driven by the availability of predator, meaning more predator, more death of prey. So that's essentially the Lotka-Volterra type interactions that we just discussed. So we'll go open in the dialog boxes. So let's start with the predator, and you'll see that the units, it's a level variable, so it's a control variable. It's a state variable, and it has units of foxes. Okay, and it's got its own equation here, net birth minus net death. Okay, so it's fairly straightforward. It's got an initial value of initial predator, and if you click on initial predator, you will see it has units of foxes. It's a constant, and it's 100. Okay, so that's the initial value of the fox population. It's 100. Okay, let's move on to the net birth, and the net birth it's got units of foxes per year, and is found by multiplying the coefficient A times the population of predator times the population of prey. Okay, and so that's pretty straightforward. And if you go to the death of predator, it's simply the coefficient B multiplied by the predator availability, the population of predators. It's got units of foxes per year as well. And let's move on to the prey. Oh, wait, let's do A and B. A, it's the intrinsic growth rate of the foxes, and you can see here that it's got units, and I wanted to stop here at the units for a second, just to see how these are calculated. It's at the end it has units of 1 per year per rabbit, but it's essentially, so you know how it's calculated, it's the number of foxes born per year, per unit fox, so per unit fox present, and per unit rabbit. So that's how it works out, and it's got this value as we discussed previously. Okay. We can look at the coefficient B, and the coefficient B it's got units of 1 per year, but that's essentially the number of foxes per year that die per unit fox. Okay, and those are the units here. Very well. Now we can move to the prey equations. And again, the net birth minus the net death will give you the population of prey. The prey it's got an initial value called initial prey. It's a state variable. It's got units of rabbits. And if we go to the initial prey, you will see the value there is 1,000 rabbits to start with. If you look at the net birth, it's essentially a first order dynamics. It's the coefficient C times population of the prey. It's got units of rabbits per year. Okay, and if you look at the net death of prey, it's second order dynamics. It's the coefficient D multiplied by the population of predators, the population of prey. It's got units of rabbits per year. And you can see the values of C and D. Again, the growth of rabbits is simply units of inverse year, or rabbits per year per rabbits. And the coefficient D has units of rabbits per year per unit fox per unit rabbit. So it's second order dynamics. This is the value. Okay, so that's essentially the model setup. I wanted to show also something that it's key to look at. If you go to the model tab and go to settings, you can look at the settings of the model. And this model is run for 1,000 years, so from 0 to 1,000. The time step here, you can select it, but it's essentially I think we're going here at whatever 0.0078125 years is, and that's probably, I'm going to venture to say, see, this is 6 months, this is 3 months, this is a month and a half. So this is probably looking at the daily level, and I'm going to venture to say that. Please verify, just so we don't have to stop the video. All right, so we can do that, and so with this said, we can just, I'm going to zoom out of this so we can actually run the model. And okay, so this should do it. I'm going to actually fit it to screen. It's probably just as well. Okay. All right. So, and you can see that I've sort of pre-selected a couple of the plots, and we're going to see those. So I'm going to run the model, and just as is. And the model just ran, and then it shows a couple of graphs. I want to focus the attention. The graph here on the right is the one I had in the slides that I just showed, and I wanted to focus on this for a minute. And you can see, interestingly enough, and what I'm going to do now is I'm going to zoom into that, to this graph, so we can actually see it in detail. And so this graph shows the value of both populations, and I'll show you in a second how to generate these graphs as a custom graph. But essentially, what you have is it's what we said before, is that the predator population, which is in blue, and the prey population, which is in red. So these are the foxes, and these are the rabbits, are oscillatory, okay, from the very beginning. So at time 0, you have 100 foxes and you've got 1,000 rabbits, and they start to interact. And then what you can see is this very interesting interaction in which, and at the very beginning, both species can grow. So the foxes can grow, and so can the rabbits. And what starts happening is that and they grow because they have an intrinsic growth. They can, there are rabbits available for the prey to grow, and rabbits have a natural way of reproducing, so they both grow. What starts happening is that as the foxes start getting more and more numerous, they start preying more and more on the rabbits, and then the rabbits start decreasing. Okay, and then you can see how the rabbit population takes a dive as the foxes continue to grow, because they just prey on the rabbits. What happens is that then the foxes start running out of rabbits to grow, and then if the rabbits drop too high, foxes are not going to be able to sustain the growth, and then the foxes start to drop. As the foxes start to drop because there's no rabbits, actually the rabbits start to recover because there's less predator, so that affects their growth, and they start growing. And then you start falling into the same dynamics. As the rabbits grow, then the foxes are able to pick up, and then again the same dynamics. Foxes grow too much, rabbits start running out, then foxes start running out, and then you have these sort of staggered, ups and downs for the foxes. And this is the cyclical, these sort of dynamic equilibrium that we refer to in class. Now, another plot that can be generated is the one I have here in the bottom, and I thought I'd show this. This is what's referred to as a phase portrait, and you can generate this plot by simply not plotting rabbits and foxes over time, but plotting actually rabbits and foxes together in the same plot. And what you get is this elongated shape. And if you think about what's happening here, is that each point in the two graphs, so let me toggle back here. The way that this plot is generated, just so you know, is that you can actually take every single time record, from 0 to 1,000. You have 1,000 data points. Each data point has a value for the population of foxes and a value for the population of rabbits. You can actually plot those two together, and what's generated is this phase portrait. And then what you can see is that it's this cyclical behavior, and what you have here is it's essentially an elongated shape that denotes sort of 4 areas. Okay, there is the first segment, which is a segment in which both the predator and the prey grow. Okay. And this is the phase in which they grow together. Both predator and prey are going up. What starts happening is that at some point, the rabbits start to fall, even though the predators continue to grow. And that's this receding limb of the phase portrait. Then you get to a point where they both decrease. The foxes and the rabbits, both predator and prey, go down. So you were in this path. And then you get to a point where actually the rabbits start to grow, but the predator is still decreasing. Okay, and this is a cycle, and then the cycle is repeated again, and repeated again, and repeated again. Okay, so these oscillations up and down essentially reflect this phase portrait. I also wanted to show you something that I noticed when I did this model, is that if you go to the model settings and you decrease this, from you go from you're not going to do it on a yearly basis. So let's do it every month and a half, or maybe every 6 weeks. Actually 3 weeks. Here, let's do that. Let's see what happens to this. And I'm gonna simulate this again, and I'll override it. I mean, you guys know this already. And I think one thing I'm going to do is that I'm going to zoom again back out to fit to screen, just so we can see. Now, it might be imperceptible, but you can see that these lines are a little bit thicker. It's that the resolution of the model, when it starts getting coarser. Let me actually make it even coarser. Let me go to 6 months, you know, and run it again. Overwrite it, and you can see that the face portrait, it shows the cycle, and you can actually see where the cycle starts right there, and where the cycle ends. And let me zoom to that graph, just so we can see what's going on. And see, you now have a essentially the start, and I'm not sure if this is the start or the end, but I would venture to say this is a start, and then you have the sort of this spiral cycle. Now, of course, needless to say, the final resolution is more accurate. So so this is really just to show the impact of the resolution on it. But if we go back to model settings and go back down to where we had it, or thereabouts, right there. Do OK, rerun it. You can actually look at the face portrait again. Okay. See again, and it's this nicely, tightly packed, cycle. So I thought it would be interesting, and nice to see in this model. So with that said, I'm going to close this case, and we're going to move on to the next. Thanks for watching. So I'm going to stop the recording here. Okay, so we're back here in the Dropbox folder for Lecture 5, and now I'm going to discuss the Predator-Prey Advanced model. So I'm going to open up the model in Vensim and just show you a little bit of the interaction. And I think the first thing that you'll notice is that this model is a lot more complex. I will spend some time going through the model structure. Perhaps I will skip a few of the details, like going through every single dialog box to look at the units. I'll let you certainly do that, and you can see that I have here a preset graph, and I don't know if it's going to show yet because we haven't run it. The model has, again, rabbits and foxes, so foxes being the predator, rabbits being the prey. And I want to walk you a little bit through the structure and also show you a couple of interesting features that are introduced in this model for you to see how they look like. Let's start with the rabbits, and the rabbits have a rate of birth and a rate of death. The rate of birth of the rabbits, it's in this model had the specific intent of inserting a sort of a disturbance into the system. Okay, I'm going to explain to you what that is. If you go to the equation, if you go to the birth of rabbits, you will see that there is the birth of rabbits is equal to the population of rabbits times the birth rate. Okay. Plus something that here it's the test of increase, and test of increase is another variable, and I'm going to get out of this just to show you what that one is. And this is a new way to introduce a disturbance that's called a pulse. And the idea here is that in this system, in this model, there is a pulse of rabbits that's introduced after time equals 10 years for a duration of 0.5, for a duration of 6 months. So, and the size of the pulse is 100 rabbits. So the idea is that here is that there's an intervention, and the intervention is to add a sudden pulse of rabbits into the system. Okay, we're going to see what the impact of that is. So that's one of the features in this model. Now, the other thing that you notice is that the birth rate of rabbits that appears, it's now here given as a something that's referred to as a lookup table. Okay, and you will see that there is there's two variables. There's a variable that's called relative population, which we'll discuss in a second, and then there's a a notation I use, table 2, there's also a table 1 for the foxes, where essentially the birth rate of rabbits, which is given in rabbits per unit rabbit per year, so it has units of 1 per year, it's a table function, it's a lookup table function, okay? And I want to tell you how that is introduced now. Now, this relative population that feeds into the birth rate of rabbits, it's a ratio of population of rabbits per a new variable that is defined in this model as sustainable population. Okay, so the idea is that you look at the rabbits as they compare to some population, and this could be a target population, or in this case is being called sustainable population, some value, which in this model is equal to 500 rabbits, as you click back to the equation for the sustainable population. So let's see. We have a sustainable population of 500 rabbits. That sustainable population allows us to calculate a ratio of the rabbits to that sustainable population, and that tells us through a table what the birth rates of rabbit is. Now let's take a look at that table. That table is T2, okay, and it's got a format, and you can actually look at the Vensim documentation for more details. But basically, the first in brackets, the first couple of numbers here indicate the range of the table, okay, and the range of the table it goes from 0 here to 2 for the independent variable, which in this case is a relative population. So we're looking at relative populations in the range of 0 to 2, okay? And then we're looking at the tabulated value of the birth rate that is going to be somewhere between 0 and 4, okay? Now the actual values are given as a series of points: 0, 4, 0.5, 3.5, 1, 2, 1.5, 1, 2, 5, and 2, 1. And that basically means that for a relative population of 0, the birth rate of rabbits is 4, okay? For a relative population of 0.5, it is 3.5. For 1, it is 2. So for a relative population of 1, when the population of rabbits is equal to that sustainable value, it's 2. Now, if the population of rabbits exceeds the relative population by 50%, so that their ratio is 1.5, the birth rate of rabbits drops. And if it reaches 2, so if it doubles, then it reaches a value of 1. Okay. Now the units of this, of course, are in. If you go back to the birth of rabbits, are in rabbits per year. Okay. So if you multiply, if you look up the table, that's going to allow you to calculate the birth rate of rabbits. And the birth rate of rabbits feeds into the birth of the rabbits. Okay. Jointly with the pulse. So essentially, what's happening here, if you think about it now, if you put everything together, is that the rabbits grow because of two things. There's this increase, the pulse, and then plus this birth of rabbits. But the birth of rabbits is dependent on how the rabbits compare to this sustainable population, this target, which in this case is 500 rabbits. Okay. So that tells us a little bit of the dynamics of the growth of rabbits, and that's a little bit of a more complex picture that we had before. Now the death of rabbits, it's handled here in slightly different manner than we did with the previous predator-prey model. Here the death of rabbits, it's going to be dependent on, and this is another introduction, because these rabbits are being hunted, okay? So let me actually walk back through that. The rabbits are being hunted by the foxes, okay, for eating, but that rate of consumption of rabbits, which leads to their death, it's driven by a dietary requirement of foxes, and we're going to walk through that in a second. So If we look at the dietary requirement of foxes, it's got units of rabbits consumed per each fox per year. That value is 25, and I put a little comment here. So this is the number of rabbits eaten per fox in a year. Okay, so that's the requirement, and so that requirement feeds into the hunt for rabbits, which is the number of foxes multiplied by the dietary requirement of the foxes. So that when you multiply those two, you get units of rabbits per year. Okay, so that gives you this value, and that is going to result in the death of rabbits. Now, the death of rabbits, so rabbits can die for two reasons. A, they die naturally, okay, or B, they're consumed by foxes. So the death of rabbits is going to be the maximum, and this is the introduction of a function in Vensim that chooses the maximum between two values. The value of the hunt of rabbits, so this is the amount of rabbits consumed by foxes, or another possibility is you take the population of rabbits and you divide it by the average life expectancy, and that gives you another. So this will give you the natural cause, and the maximum of those two is what dictates the actual death of rabbits. Now, in this model, the average life expectancy of a rabbit is 2 years. Okay, so either a rabbit either dies after 2 years, thereabouts, or is eaten before by the foxes, and that's a little bit of the dynamic of the demise or the decrease of the rabbit population. Let's take a look at the foxes. Okay, so the foxes in this model can be born, and the birth of the foxes is handled much in a similar way as the birth of rabbits. It's essentially a lookup table where the birth rate of the foxes, it's a table T1, and it's a function of relative population. And the understanding here, and this is very similar to the one we saw in the Lotka-Volterra model, is that the availability of rabbits, its relative population, it drives the ability of foxes to grow. So what you have here now is that the relative population drives the birth rate through this table. In this table, let's take a look at it now. It's a table. It's the same format. You have a range here in brackets. So the table goes from 0 to 2 again in the relative population. So we're assuming that the population of rabbits is always somewhere between 0 and twice the sustainable value of this 500 that we have there, but we can change that. And then the T1, the growth of foxes, it's somewhere between 0 and 0.6. Okay, and then if you look at the values, and these are actual values: 0, 0.5, 1, 1.52, and then for the growth rate, 0, 0.12, 0.25, 0.27, 0.3. So that's the range in which the growth rate of the foxes moves. Okay, so that dictates the foxes, and then the foxes die also, and the only reason that foxes die is natural causes in this model, and it's driven by an average life expectancy of 4 years. So that's after 4 years these foxes die, or at least on average. So that is essentially a rundown of this model dynamic. You can see it's a lot more involved. So let's take a crack and run it. And so if you do that, here you have the preset graph for the rabbits, and then you can see interestingly enough that it's prior to. And let me actually zoom into that. I'm going to zoom maybe to 100. No, it's too little. We zoom to 200, and that's going to be big, but at least it'll allow me to see the graph in a lot more detail here. Okay, so you can see actually that you get again this oscillatory behavior. Okay, goes up and down. It starts at 500, so it starts at the population. And then remember that we introduced, and I'll show you the graph in a second, a pulse at 10 years. We introduced this pulse that was 100 rabbits, so it went up, and then it starts, oscillating after that. So the reason it goes up is because of the introduction of that pulse. Okay, so let me zoom back to the fit screen, and let's take a look at the graphs at other for other variables. So if we look at so the rabbits will do essentially that we just saw. Okay, that's the same graph. Let's look at the foxes and see. Let's take a graph of the foxes, and just shade them there so they appear there. So the foxes also, because of the introduction of the rabbits, they seem to be dormant or more or less steady at the beginning at 40, their initial value, and then they start to oscillate. Okay, the oscillations are not as big, and it goes up to maybe 42 rabbits, and then comes down back to 40, and then it goes back and forth. But it does introduce an oscillatory behavior. I think it's probably interesting to look at the test of increase in a graph, and you can see the pulse here. Okay, so the pulse was at 10 years for half a year. So for 6 months, you introduce 100 rabbits, and then the pulse died away. So it's a sudden introduction of rabbits into the system to see how they affect the remainder of the dynamics. Okay, and you can actually start playing around with it a little bit if you want. Let's see, what else can we see? Let's take a look at the. We can actually do anything. Let's look at the hunt of rabbits and see how hard they're being hunted. You can see here that this is the rabbits hunted per year over time, and you can again see this oscillatory behavior. Typically, when you have a system where one of the variables is oscillating, that means that probably the remainder of the variables are going to be oscillating too. It's only natural that if things move in, shake in one direction, they shake also in other variables. They don't have to oscillate in sync, as we saw in the Lotka-Volterra model. There is a lag. There could be a phase or a lag between the oscillations, but it will oscillate. We can look at the let's see. We can look at the birth rate of rabbits, for example, and we can do this pretty much for any variable. We can click and look at the plot very quickly. The birth of foxes, same deal. Again, oscillations. They don't have to be all nice, but as long as they're regular, they sort of look the same. You can do that. I think one thing that I wanted to show in this model that I didn't show in the previous one is how to build those plots. So you can actually go to, if you go to Control Panel. One thing before we do this, sorry, is let's look at the model setup. It's always good to look at the setup. And again, it runs for 100 years. It's running at a time step of 1/10 of a year. Okay, and you can actually change that if you want and see what the impact is, and you can play around with this a little bit more. So I wanted to say that. But let me go to the Control Panel and just see how you can define. You have all these variables here. You can define graphs, and I defined a graph that's called foxes and rabbits, and this is the same graph that was defined in the previous one, but I want to show you how it looks like. And if you click on it, and it'll display it, and this is the one that shows the the populations together. Okay, and you can actually edit all these things. You can edit the time span. You can edit and I'll show you how to do that in a second. But this is essentially the graph that looks at both populations, and you can see then the oscillations of one versus the oscillations of the other, how they're not completely in sync, etc. Okay. Now I wanted to show you if you select from the Control Panel, select graphs, and select the graph that you want to look at, and say modify in this case. You can see here how to set up this model. You can give it a name, okay, and I call that foxes and rabbits. You can give it a title, which is the legend that appears on top of the graph, okay? And you can, in here, you can essentially put in all the variables that you want to plot together. And, it allows you to do up to 6 here. I just wanted to do the 2. You can modify the horizontal axis. In this case, it's time, okay? You can plot time. and you can select the range. And I just set 0 to 100 years. I can change that and see what it looks like. It's not not a huge deal. And then you can modify all that and then just redo the plot. So what happens, for example, if we do from 0 to 200, just for the sake of an argument, and do that, and then close here, and then you essentially redo the simulation, okay? And we redid the simulation. Let me pull the plot out again. Oh, I think I had it. I probably just had it displayed. I may not have to run this, and then let me get rid of the old one. This is a new one, and oh, you know what? What happened is that we don't simulate past time. So that was a silly exercise. So let's actually redo the simulation now. Going to settings and running to 200. Okay. Now we can rerun, and then we can actually simulate again simply. Just say yes. So it replaces, and you can actually display the new graph. See, and you see revised, sort of the same graph. It's just it extends to 200. So I thought I'd show that on this case, as well as let me close this, as well as give you a summary. So we looked at the pulse in the test of increase. We looked at lookup tables for the birth rates of foxes and rabbits, and we also looked at the max value as a function to select between two variables. Okay, so this model has those little upgrades that you can look at. So you can look at all these results. You can modify. One thing you can do also with this model is you can do an input-output object and do the synthetic simulation. Remember, this will allow us to you can overwrite it, or you can change the number. And now, see, you can turn some knobs. Okay, you can turn the sustainable population of rabbits. You can play around with the expectancy life of foxes and rabbits. You can with the dietary requirements, and you can see how the graphs vary. The other thing you can do as well is you can actually go to each of these boxes, and actually I changed it dramatically, but I just wanted to let me actually look at how I think I went too far. And of course, you can see that you start getting garbage when your things are too unrealistic. So that let me take it down back to 25. Let's see. You can actually click. Let me do that. If you click on the arrow, you can just fool around a little bit with the size, and we're using 25. I let it vary from 0 to 200, but I can just say let's just vary between 0 and 50 if you want to restrict it, and it's and then then it will give you less leeway. You can do the same with all of these. 0 and 10 for the expectancy of rabbits. It's probably okay. For foxes, between 0 and 20, that's probably okay. And for sustainable population, between 0 and 3,000, which is probably fine. It's and then you can start running and see what the impact is. Okay, so it's a nice predator-prey model for you, and I hope you can play with it and learn some more. And we'll move on to the next example now. Okay, so we're back here in the folder for Lecture 5, Social Interactions. Let's look now at the Catastrophe model. So I'm going to open that in Vensim. This one is interesting. I think I want to say no here. Let's say no. I think just for the scaling. Say no again. All right. Yeah, this will probably do it. Let me max out the screen. And so this model it's interesting. It's got three cohorts: a cohort of young people, cohort of adult people, and a cohort of elderly people. And of course, these cohorts exchange. One matures to the other. So I'll walk you through a description of the model, and we'll look at some of the units and see what the results are. But essentially, the young are born, okay, and the born is driven by a birth rate, and it's driven by the availability of adults. So a young population doesn't reproduce, adults reproduce, and the young become adults through maturity, and we're going to see a little bit of how that happens in the dialog boxes. The adults, further age and become elderly, and the elderly pass away. Okay. Now, the reason this model has a catastrophe is that because it has it's got a flux out of the adult pool, the adult population pool. It's called a catastrophe, and I'm gonna look at that first, just to illustrate what the issue is. And the issue is that there is a pulse. In year 2005, it lasts for a year, and it loses 100,000 adults. So there is an event that causes 100,000 immediate deaths in the adult population. And the idea of this, of this model is to see what that does to the overall population. So let's walk a little bit through the entire model, and let's start with the young. So the young are essentially they're born, and then they become mature, or they can actually die. So this model actually has, the units of this are people. So this model actually has a death of young people. So there could be an accident or something that causes young people to die. Okay, so there's a young people mortality rate that's given, based on whatever demographic data you have, or whatever data you have, and there's a maturity, which is it's a factor that is used to define when there is a transition in being from young to adult. So this defines a period of maturity, which in this case the period of maturity here is 25 years. So 25 years is in this model, it's the period of time it takes for a young person to become an adult. So you become an adult at 25 years old, and for the purposes of this model. Okay. The young can die. Okay. As I said again, or they can become mature, and those are the two ways that young people decrease stock. Okay. So let's look at adults now. The adults are fed by the young through maturity. Okay, so if you look at the adult equation, there's maturity, feeds into that. Then adults die either of old age, or through a catastrophe. So if you look at the schematic again, the adults become old and become elderly, or they die. Okay, they can die, or they can die due to this catastrophe, which we just indicated was a pulse. Okay, 100,000 people are removed in 2005 from the pool of adults. Then if we look at the elderly, okay, the elderly are fed by aging adults, and then are decreased due to natural deaths. Okay, and the natural deaths are driven by a so-called final period, which is let's take a look at that variable. Final period, it's a period of years. So after they become elderly, actually I don't think there's a period of aging here that I didn't go through. 60 years. So at 60 years, an adult becomes an elderly, and 30 years after that, it can be considered to be, to die due to natural causes. Okay, so that's the way people die of old age. If there's an additional auxiliary variable here, there's a total population that is calculated by adding adults, the young and the elderly, so you can actually keep track of that. So that's essentially the picture. Okay. In a nutshell, you have a 3-cohort population of young, adults, and elderly that mature over time. So the one becomes the other. But in the middle, there are extracts. The young can die, or they become mature. Okay. The adults can die, they can become old, but there's also a catastrophe that takes out 100,000 people, and then the elderly can essentially die of natural causes by themselves. The adults produce offspring through births, so that's another variable, and those are essentially the dynamics. 25 years of maturity, 60 years to become an elderly. There's a catastrophe. One thing that I didn't mention was the initial values. And if we go to the stocks, so the young initial population is 400,000. For the adults, it's 500,000. And for the elderly, it's 100,000. So that's the initial state of the population. And if you look at the model settings, you can see that it's a 100-year model from 2000 to 2100. Time step is 1 year. You can change that, but that's pretty much the setup. And you can then run the model. So you can just do a simulation, and the simulation is done very quickly. And now we can go to the graphs and see what happens. So let's take first a look at adults. I think that's because those are the ones that undergo the catastrophe. And if you look at the graph for adults, you can see here what we were referring to. The adults started 500 during the first 5 years until 2005. The adult population is going down. That probably means that a lot of them are becoming old. Okay, but then all of a sudden the population takes a dip. It loses 100,000, and then after that it sort of starts recovering over time, and it sort of plateaus out at a little bit over 400,000, and that's the adults. Okay, we can look at the elderly. Okay, and look at the graph. And the graph for the elderly is continuously increasing. So what's happening in this population is that the adults are aging, and so the population is elderly is going to plateau somewhere near 200,000 people. Okay, so because of adults, and it's interesting to see that the catastrophe that adults undergo doesn't seem to affect much, the elderly population. Let's take a look at the young. Look at the young and graph it. It's interesting because this actually it's very reflective of what happened. This actually picks up on the signal from the adults. The younger are, they're born, they start growing and becoming more as adults reproduce. Then the adults in 2005 take the hit for the catastrophe, and that makes the young population drops after that effect disappears, and then this sort of plateaus out at started at 400,000. Remember, the young, it ends up being less than that. So the lasting effect of this catastrophe is that the young population never quite recovers. Okay, and so the effect keeps going on. And if you look at the total population graph, so now this is the the total, the young plus the adult plus the elderly, you can see that the population as a whole does tend to recover. There's it grows at the beginning of the first 5 years, and it takes the catastrophic hit, and then it starts growing. Now, what we saw is that this growth is primarily driven by the adults that were larger to begin with. They were 500,000 to begin with, becoming elderly. So the lasting effects is that you have a population that recovers from the catastrophe but becomes older on the average. Okay, so that's an interesting demographic effect of this catastrophe. Again, with this model, you can do many of the same things that you can do with other models. You can create input-outputs. You can create custom graphs. You can do variable inputs. So I'll let you play with this and look at how these cohorts interact. You can fool around a little bit with the maturity and aging periods, with the death rate. So you have a whole host of variables here that you can toy around with. So hopefully you'll be doing that. That will conclude the discussion of this model, and I'm going to move on to the next one. So we're back here to our Lecture 5 Social Interactions directory, and we're going to be looking now at the epidemic model. So I'm going to open that up and fire it up in Vensim. Again, no. Let's look at this model scaled as it is. And so this model is a slightly more sophisticated version of the, again, 3 cohorts, susceptible, infected, and recovered or recuperated stocks that we saw earlier. And let me walk you a little bit of what's been included in this model so you can take a look at it. Let's look at the susceptible. Susceptible population can there's a couple of ways that the susceptibles can go. Susceptibles can get vaccinated, and if they become vaccinated, then they're automatically recovered. So they're, again, they won't, they won't become ill, or they can become ill and infected and become part of that stock. Okay. The infected can become cured. Okay. And so they can just become cured, and then they become recovered, or they can die. Okay, and there's a rate of mortality there. We're going to see those in a second. The recovered occur because infecteds get recovered, because susceptibles get vaccinated. Now the recovered can get, in this model, can get re-exposed to the disease, and then they can become susceptible again. That sort of triggers the cycle again. Let's take a look at some of the variables here. Let's take a look at the susceptibles and what goes out into that. Let me look at the equations. So susceptibles are equal to the exposed minus the ones that become ill minus the vaccinated. Okay, there's an initial value of 900 in this population, and the units are individuals. Okay, individual. Let's look at the possibility of being vaccinated for a susceptible. So the vaccination, it's essentially it's the units of individuals per month. So it's a first order process. So it's a product of the susceptibles times a rate of vaccination. And let's take a look at what this rate of vaccination looks like. The rate of vaccination here, it's a ratio of the people that become ill as a fraction of the susceptibles. Okay, so whatever fraction of susceptibles become ill times the availability of vaccines. Okay, the availability of vaccines is another variable here that is simply it's a non-dimensional factor between 0 and 1, with 0 meaning that there's no vaccines available, and 1 which means all full availability of vaccines. There's no limitation. So here, what this is saying is that 50% of those that can be vaccinated will be vaccinated. Okay, so that works into the rate of vaccination. So that's essentially the story with vaccines. Now, susceptibles can become ill. Okay, in doing so, it's essentially this here is the SIR fraction of the model. The inputs of susceptibles into the infected pool is the product of the susceptibles times the infected times the rate of infection. Okay, so there's this will be the beta rate. This rate of infection is the beta rate that we saw earlier. Okay, that rate of infection, let's take a look at it. It's a constant, and it's equal to 0.001. Okay, in this case. So once they become infected, the infecteds can become recovered through a rate of recovery. Okay, this is what we call the gamma in the SIR model. It's got units of 1 per month, and so if that happens, they can become fully recovered, they can become cured, but they can also die, and there's a rate of mortality here, so the dead are the product of the infected times that rate of mortality. Is a first order process. So this wasn't included. The infected in the SIR model can only be recovered, but they cannot die. In this case, they can. So this is a little bit more more involved model. Okay. Um, so the once they, if they're cured, they become recovered. The recovered are fed by the vaccinated, um, and now the recovered can become exposed. Okay, so there's a rate of exposition here, um, which means that they can reacquire the disease and become susceptible. Okay, so that's how the loop is closed. Oh, here there's a little auxiliary variable to show the the total population. So okay. So let's look at the model setup, and if you look at the settings, this model is run from 0 to 20 months, okay, and time steps of 1 month, okay, that's fine. So this is a the study over a 20-month period, and if you look at the initial values, there's 900 susceptibles to start with. There are 100 infected, so that's the disease starts with 100 people, and there's 0 recovered. So there's no one's recovered at the initial point. Okay. So with the model setup, you can go and run it. Go to simulate. Runs very quickly, and then we can just start. Start graphing, so let's start doing that. Let's see what happens to the susceptibles. Remember, they started at 900. If you look at the graph, the susceptibles start at 900. They drop because they become infected. So they're no longer, become infected. They're no longer susceptible. And then I guess as we'll see the other dynamics, but it seems that the susceptibles start picking up again. So there's got to be some recoveries. Okay, so that's what it appears here. Let's look at the infected. What happens to the infected? And as we saw, essentially there was a peak in the infection. So the starts at 100 and then goes up to nearly 200 and then starts dropping as people get recovered over the 20-month period. And if you look at the recovered, same story. It starts at 0, but as people start getting recovered, it grows and then it sort of tapers off as the system stabilizes. You can look at the total population and graph it, and you can see that actually the total population started at 1,000. The effect of the disease, of the epidemic in this case, is to make the total population drop to just a little bit over 850 people. So there is that lasting impact of the epidemic in terms of and we can look at the number of deaths, and you can see the number of deaths are here. So there's about 10 people dead, and then it goes up to 20, and those are and then then it sort of graphs out until the end. There's very few people dying, but it does add up to the 100 plus people that were lost in the process. Okay. So that's pretty much it for this model of interaction. You can play around with this a little bit. You can one thing you can do here, actually we can try it here on the fly, is to do a graph, and let's define a new graph here. Okay, and we're going to call it epidemic cohorts, something like this, and these here will be susceptible, infected, and recuperated populations. Nice little title. In the x-axis we'll put time, okay, and the minimum for the population for the time would be 0. The maximum will be 20, and that's the range. Let's select the 3 populations here. Let's look at the susceptible. Okay, that's one variable. Let's look at the infected, and let's look at the recovered or the recuperated. Okay, let's do that. Let's OK out of this, and let's display it. Select it and display it. Okay, so now you see, oops, sorry. here, and I'm gonna close this, and I'm gonna zoom on this plot. You can then let me just zoom. Oops. View, zoom. Let's zoom. Oh, it didn't. For some reason, it's not showing. So maybe I can't make this. Oh, I can make this bigger. Oh, forget the zoom. Forget the zoom, and let's make this graph bigger. I like this better. And then you can see here the three. The three that population, the three cohorts. And their dynamics. And this is essentially an interesting case because it shows how three populations or three stocks get exposed to a common phenomenon, and see how it affects the three of them. And you can see the susceptibles going down and then recovering, the infected going up and then recovering, or tapering down because of recovery, and the recoveries going up and then stabilizing as well. So that's the interacting dynamics of these three. So I think I'll leave it at that. You can do many more things with this example, and I'll let you play with it. Hopefully you've enjoyed all of these cases, and we'll keep discussing some of these features next week. I'm going to stop this now and go back to the lecture.